In 1911, Ernest Rutherford proposed a new atomic model, but it had a terrible flaw that would make all matter unstable. Then, Niels Bohr showed up. In this video, we will encounter 6 of the participants in the famous Solvay conference of 1927, most notably Niels Bohr. In 1909, Rutherford was already an accomplished physicist. As one of J.J. Thomson's great students, he had a distinguished career studying radioactive elements and received the Nobel Prize in Chemistry in 1908. Rutherford created a prestigious lab in Manchester, where his assistant Hans Geiger invented a radioactivity detector that would later become the famous Geiger-Müller counter. Rutherford asked Geiger to work with an undergraduate student named Ernest Marsden, bombarding thin foils with alpha particles and measuring their arrival on the other side. The surprise was that some alpha particles bounced back in a way that could not be understood within the accepted atomic model that Thomson had proposed in 1904. In the summer of 1909, Geiger and Marsden published the mysterious results of their experiments, indicating that a small fraction of the alpha particles falling upon the metal plate have their directions changed to such an extent that they emerge again at the site of incidence. There is a famous quote in which Rutherford described the phenomenon in simpler words. It was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it came back and hit you. 2 years later, and after careful calculations, Rutherford found a solution. Challenging the atomic model of his mentor, he found that the behavior of the alpha particles could only be explained if the positive charge of the atom is concentrated in a small nucleus and the negative electrons stayed at a great distance around this nucleus. To compensate for the electrostatic attraction, the electrons could not be at rest. Borrowing ideas from celestial mechanics, the electrons must orbit the nucleus just like planets around the Sun, leading to the most popular depiction of the atom used as a representative diagram until our days. This so-called Rutherford atomic model explains the results of the Geiger-Marsden experiment, but it has a significant problem. If the electrons orbit the nucleus, they continuously accelerate, otherwise they would move in a straight line. And according to Maxwell's electromagnetic theory, this acceleration produces radiation that would be emitted away. This is in fact how antennas work. This effect would make the electrons lose energy and rapidly spiral down into the nucleus. Let's calculate how long it takes for an electron to fall into the nucleus. Consider the simplest atom, hydrogen, with a single electron orbiting the nucleus of the opposite charge at a distance r. From Newton's second law, the centripetal force mv squared divided by r is equal to the electrostatic attraction given by Coulomb's law. From here, the speed of the electron is given by this expression. The total energy of the electron is its kinetic energy plus the electrostatic potential. The negative sign here indicates that the potential is attractive. Using the relation for the speed found above, we find that the total energy only depends on the distance to the nucleus. Let us now describe the process of energy loss by radiation. The power radiated, or energy loss by a charge E with an acceleration a, is given by Larmore's formula. The negative sign indicates that the energy of the electron decreases with time. Using the centripetal acceleration v squared over r, we find this expression. Dividing both sides by the whole expression on the right-hand side, we can write 1 equals all this combination of factors. Now we use the expression found above for the energy. Taking the derivative with respect to time, we find an ordinary differential equation for the radius. Finally, we integrate over the time that it takes for the electron to go from its initial orbit at r equal r0 to crashing into the nucleus after some time t0. Let me just clear the screen here. The left-hand side is simply the time t0 that we want to find, while the integration on the right-hand side is a trivial polynomial. To evaluate this final expression, we can use that the size of the hydrogen atom was known to be around 1 angstrom, or 10 to the minus 10 meters, so the radius would be roughly half of this. Plugging all the values, we find that the electron would spiral down into the nucleus in about 10 to the minus 11 seconds. This quick calculation shows that in Rutherford's atomic model, the electrons would spiral down into the nucleus in less than a nanosecond, making all atoms unstable. The same year in Denmark, Niels Bohr received his doctoral degree in theoretical physics and prepared his move to England, where he would join J.J. Thomson's lab. His love for physics was for some time shared with football. During his university years, Bohr and his brother Harald played professionally, Niels for a whole season in 1905 and Harald even as part of the Danish national team. Harald Bohr studied mathematics, but he was famous in Denmark for his performance with the Danish team in the 1908 Olympics. Niels decided to focus on atomic extractor instead. I would like to take a minute to thank Surfshark, the sponsor of this video. Surfshark is a VPN system that solves a problem that I have had in particular this year. I have, for the first time in a while, traveled abroad several times. And with this I discovered that plenty of online content that I took for granted at home was not available in the countries that I visited. Here's when a virtual private network, or VPN, comes to rescue, because it allows you to virtually change the location of your device so you can navigate the web from anywhere in the world. With Surfshark, you simply download and install the VPN app on your device, connect using your account, and select the region you want to connect from. And voila, get immediate access to all your favorite content, including streaming platforms. And in addition to this, you can use your account on all your devices. Get Surfshark VPN at the link in the description. Enter the promo code JK0 and get 4 extra months for free. Also notice that there is a 30-day money-back guarantee, so you can try it risk-free. Again, the link is in the description below. Thanks to Surfshark VPN for sponsoring this video. And talking about traveling abroad, let's get back to Niels Bohr, moving from Denmark to England. After moving to Cavendish Lab in Cambridge, Bohr and J.J. Thomson did not get along. Bohr was young, brilliant, and loved to intellectually challenge those around him. But Thomson was not having any of that. Bohr wanted to research electrons. Thomson had lost interest in the topic. During the so-called annual Cambridge dinner in 1911, Rutherford visited Cavendish Lab. Although they did not formally meet, Bohr was fascinated by Rutherford's work. A few weeks later, through an old family friend, Bohr found his way to Manchester to meet Rutherford in December of 1911, who had recently returned from Belgium, where he participated in the first Solvay conference. Bohr was very excited with the summary of the conference that Rutherford shared, and Rutherford was really impressed by Bohr's ideas. Rutherford liked Bohr despite his prejudice for theorists. He would later remark, "Bohr is different. He's a football player." Given his disappointed experience with Thomson, after some arrangements, in March of 1912, Bohr moved to Rutherford's lab in Manchester. Bohr came with many ideas about electrons, but the new mentor challenged him back and asked him to strengthen his experimental knowledge. Geiger and Marsden were Bohr's instructors on experimental methods for radioactivity, and he became friends for life with the Hungarian chemist George de Hevesy, who taught him radiochemistry. This experience was crucial for Bohr. During these discussions, he discovered that radioactive properties of the elements arise from the nucleus, while the distribution of electrons around the nucleus is responsible for their chemical properties. This insight led to one of the early understandings of why the chemical elements are organized the way they are in the periodic table. The radiochemistry lessons from the Hevesy also led Bohr to the idea that radioactive decay will make an element move within the periodic table. During 1912, Bohr came out with the following reasoning. During the last decade, experiments exploring physics at the atomic scale showed that classical rules were insufficient, and some wild guesses appeared to point in the right direction. Planck quantized energy and produced the correct blackbody radiation formula. Einstein quantized the energy of light and explained the emission of photoelectrons from metals. Einstein's quantization of the vibrational energy of molecules produced the correct specific heat for solids. Some deviations were observed, but Peter Debye quickly fixed this by a careful extension of Einstein's model for solids. So maybe, Bohr thought, a new arbitrary quantization rule could stabilize the electrons in Rutherford's atom. One of the keys was Planck's constant. Planck and many others refers to it as the quantum of action because of its units. In Lagrangian and Hamiltonian mechanics, the action is the fundamental object that allows deriving the equations describing a physical system. Defined as the time integral of kinetic minus potential energy, the action has units of energy times time, just like Planck's constant. But these units can also be written as mass times length squared divided by time, which is what we use to measure angular momentum. Bohr wondered, what if Planck's constant could be used to quantize the angular momentum of electrons in Rutherford's atomic model? Just like Planck did for blackbody radiation, Einstein did for light, and Einstein-Debye did for molecules in solids by restricting the energy to be E equals nhν. Niels Bohr wrote the so-called generalized angular momentum J equals nh, where n is a positive integer, now called the principal quantum number. This generalized momentum is a concept borrowed from Hamiltonian dynamics, where p sub phi is just the angular momentum, usually denoted by L. For a circular orbit, this reduces to 2 pi times the angular momentum L. Bohr's quantization rule is most commonly written as L equals n h bar, where h bar is just Planck's constant divided by 2 pi. What Bohr proposed was that electrons can only orbit the nucleus so that their angular momentum satisfies this quantization rule. So how does this quantization rule stabilize the electron around the nucleus? In these so-called stationary states, the electron will simply not radiate. Yes, Bohr made electrons stable by simply imposing that they cannot radiate, contrary to Maxwell's electromagnetic theory. If you feel that this is arbitrary, you're not alone. Bohr himself recognized that this was just a what-if approach, and then Bohr explored the consequences of this arbitrary quantum condition. For a point particle like the electron, following a circular orbit, the angular momentum is simply the product of its mass, speed, and radius. Using the expression for the electron speed found earlier, we get a formula relating the radius and the quantum number n. Solving for r, we find that the electron can only take discrete orbits around the nucleus that grow quadratically with n. The closest orbit to the nucleus corresponds to n equals 1. Plugging all the constants, this radius is equal to 5.3 times 10 to the minus 11 meters. Notice that this value is remarkably similar to the estimated size of atoms mentioned earlier. This smallest distance of the electron around the nucleus is called Bohr radius. Let us now check the electron's energy. Replacing the general form of the radius into the energy formula found earlier, we get that the total energy that an electron can have orbiting the nucleus is given by this expression, where the negative sign indicates that the electron is bound in orbit around the nucleus. The lowest possible energy level, called the ground state, corresponds to an electron in the level n equals 1, which has an energy of minus 2.2 times 10 to the minus 18 joules, or minus 13.6 electron volts. This number is very important because Bohr knew from his lessons with the heavisy that it takes close to 13 electron volts to ionize the hydrogen atom. In other words, his quantum guess led Bohr to mathematically derive two crucial quantities in the hydrogen atom with remarkable accuracy. The agreement made him confident that he had just unveiled another quantum secret, despite having no clue about the physical meaning of the quantum number n, other than being a label for allowed states within the atom. I would like to mention that a very similar idea was published the year before by John Nicholson in England. Nicholson also quantized angular momentum to characterize new chemical elements that he proposed to explain some unexpected spectral lines in astrophysical observations. In the end, the line of these apparent new elements turned out to be produced by highly ionized elements like iron and oxygen. Nicholson's model was conceptually flawed. For instance, his model required neutral hydrogen to be a compound with 3 electrons. His atoms were also unstable. Despite the imperfect model, Bohr found it highly influential because it made him consider the application of his own atomic model to the description of spectral lines. Bohr was eager to publish his results, but he decided to extend his work to make it more compelling. In the summer of 1912, he had to return to Copenhagen, but stayed in close contact with Rutherford and the heavisy. Deriving experimental quantities from his arbitrary quantum condition was remarkable, but Bohr knew that this was not enough to convince other physicists of his new model of the atom. Motivated by Nicholson's work, he then moved to one of the hardest problems in chemistry of the time, spectral lines. For over a century, chemists and physicists had tried to explain the mysterious dark lines observed initially in solar measurements by William Wollaston and Joseph von Fraunhofer. In 1859, Gustav Kirchhoff, who you might remember introduced the concept of blackbody radiation, and Robert Bunsen discovered that the mysterious lines perfectly line up with emission spectra observed when heating specific chemical elements with Bunsen's famous burner. They concluded that the dark lines are produced by the absorption of light by the corresponding elements in the sun, which opened a new window to the study of celestial objects. The physical origin of the lines remained a mystery, but in 1885, the German physicist Johann Balmer discovered an empirical formula that could predict the wavelength of a collection of these spectral lines. Each line is characterized by an integer n, while b is a constant. This formula was generalized for several lines of hydrogen in 1888 by the Swedish physicist Johannes Rydberg. This new formula contains two integer parameters, n1 and n2, and an overall factor called Rydberg's constant. As an empirical formula, there is no direct physical interpretation for the overall constant or the integer labels. The formula just works. Bohr decided to apply his results to the hydrogen spectrum by calculating the energy difference between two energy levels. Assuming conservation of energy, Bohr suspected that this energy difference would be emitted or absorbed as radiation. Although Bohr did not believe in Einstein's light quanta, he borrowed the energy-frequency relation to write the energy difference in terms of the radiation's wavelength, which becomes this expression. Now this relation looks identical to Rydberg's formula, with the difference that now Bohr has a justification for the two integer variables n1 and n2, and a way to calculate Rydberg's constant from other fundamental constants. Plugging all the values, Bohr found a remarkable agreement with the experimental value of Rydberg's constant. Bohr had discovered a new model of the atom based on quantum rules. Bohr wanted to move to more complex atoms, beyond hydrogen, but his mentor asked him to stop and publish it. Rutherford has some serious concerns on Bohr's proposal for the transitions between energy levels, but it still recommended that he should publish it because other similar ideas existed. In addition to Nicholson's model, an idea about quantization of electron orbits by Austrian physicist Arthur Haas was debated in 1911 during the first Solvay conference. Bohr learned about the details of the discussions from a copy of the conference proceedings edited by the French physicist Paul Langevin, a former student of Pierre Curie, and his own student, a French prince named Maurice de Broglie. Bohr published his complete work in 3 parts, known as the Trilogy, between July and November of 1913. These papers define what we call Bohr's atom, which was highly influential and reinforced Einstein's idea that quantum features not only applied to light, but also to matter. The great success of his model was the explanation of the spectral lines of hydrogen as light emitted or absorbed when an electron jumps between energy levels. When light is absorbed, the electron jumps to a higher level, producing the so-called absorption lines. When an electron jumps to a lower energy level, the excess energy is emitted in the form of light, producing the corresponding emission lines. In 1922, Niels Bohr was awarded the Nobel Prize in Physics for his services in the investigation of the structure of atoms and the radiation emanating from them. I should emphasize that Bohr's quantum model of the atom was based on an arbitrary quantization rule, just like the other key foundational works of all quantum theory. A mathematically consistent and systematically sound theory of quantum mechanics was still some years in the future. I have mentioned the first Solvay conference several times, which was titled The Theory of Radiation and Quanta. What I find interesting is the indirect consequences of this event beyond the conference itself. By the way, Paul Langevin, the editor of the proceedings, is the gentleman sitting next to Einstein in the famous 1927 photograph. His student and fellow editor, Maurice de Broglie, was becoming a recognized name due to his great experiments on photoelectricity with X-rays. As a wealthy prince in France, Maurice de Broglie had his own lab in the basement of his palace, where he did demonstrations for his little brother named Louis. Louis de Broglie read an early copy of the first Solvay conference proceedings when he was 19 years old. Later in his life, Louis de Broglie wrote, "I was swept away by my enthusiasm for the problems discussed at the conference, and I resolved to devote all my efforts to understanding the true nature of the mysterious quanta that Max Planck had introduced 10 years earlier."